Now we'll start the next topic, that is types of recursions. So here are the list of types of recursions. I'll be discussing each of them one by one by taking some examples. See, the tail recursion is the first one, then head recursion, tree recursion, indirect recursion, and nested recursion. So we'll look at them one by one. Let us start with tail recursion. Yeah, here is the first recursion, that is tail recursion. We have already seen this type of recursion. This function already I have explained in the previous video. Now it is a tail recursion. So what does it mean by tail recursion? If a recursive function is calling itself, and that recursive call, this is called as recursive call, and that call is the last statement in a function, then it is called as tail recursion. After that call, there is nothing. It is not performing anything. So it is called as tail recursion. For example, this is fun and taking some parameter n, and if n is greater than 0, the similar one I am writing, and there are some statements inside, then the last thing is it is calling itself by a reduced value of n. See, what all it has to do, it is performing first, then it is calling itself. So in this example, I have just written printf, but there may be a lot of things a function may be doing. All those things it has finished, then it is making a call to itself. So if it's a last statement, then it is called as tail recursion. So this means that all these operations will be performed at calling time only, and the function will not be performing any operation at returning time. Everything is performed at calling time only. So that's why it is tail recursion. Now suppose there is something written here, plus n, means along with the function call some operation is done. Then if this is the case, then when this operation will be performed, this will be performed at return time, because unless the result of this function is known, addition cannot be done. The value of the function is added with n. So this addition can be performed only at returning time. So in this function, there is something remaining that has to be performed at returning time. So it cannot be a tail recursion. Tail recursion means at returning time, it doesn't have to perform anything at all. So this is a perfect example of tail recursion, or else if I remove any processing here, then it is a tail recursion. Now next, I will compare tail recursion with loops. Now comparison of tail recursion with a loop. So first and the foremost thing I have to tell you is that every recursive function can be written as a loop or vice versa. Every loop can also be converted in the form of a recursion. But now let us compare tail recursion with loop. See, this is a tail recursion. Already you know the answer in the previous video. Already I have traced this one and shown the output. If we call this function by passing 3, so it will print 3, 2, 1. And it will stop when the value of n becomes 0. So it will print the values 3, 2, 1. And it will print in calling phase. Now same function, I want to write it using loop instead of recursion. So I will write on the function here, void fun, which takes parameter n, and the first thing is n greater than 0. I will write n greater than 0, but instead of if, I will write it as while. Then inside this printf statement, this is printf percentile d and some space n. Then calling function again itself by reduced value of n. So let us do n minus minus. That's it. So if I call this function by passing value 3, then 3 will be passed here, then it will first print 3, then it will make 2, and again repeat. So print 2, then repeat, print 1, then repeat, it is 0, so it will stop. So this will work same as that recursion. As it is, I have converted, just instead of conditional statement, I made it as a loop. Instead of conditional statement, I made it as a loop, and instead of function call with reduced value of n, decreased value of n, I have just written n minus minus. So the function is same as that one. Output is same, and the structure also, if you see, it looks more similar. That's what. So the point that I have to tell here is that tail recursions can be easily converted in the form of a loop. Now let us decide who is efficient. In terms of time, if you analyze, this is printing 3 values and this will also print 3 values. So the amount of time spent is same. Whatever the value of n is given, if it is 3, then it is 3. If it is 5, then it is 5. So it means the time taken by both of them is order of n. So time is same. So the time taken by both of them is same. So the time is order of n. But let us analyze the space. This is a recursive function. It internally utilizes stack. So for the value of a 3, it will create a total 4 activation records in a stack. This already we have done the analysis. So for n, the space taken by this one is order of n. But what about this one? This is a loop function. So how many activation records will be created? Only one. It is not calling itself again. So the space complexity for this one is order of 1. So it will just create only one activation record. So that is constant. So we say it is 1, order of 1. That is constant. So there it is order of n and here it is order of 1. So the conclusion is, if you have to write a tail recursion, then better you convert it into a loop that is more efficient in terms of space. But this will not be true for every type of recursion or loop. In case of tail recursion, loop is efficient. And even I have to tell one more point, that some compilers under code optimization inside compiler, they will check if you have written any function which is a tail recursion, then they will try to convert it in the form of a loop. It means they will try to reduce the space consumption and they will utilize only order of 1 space. So your function will be converted into object code just like a loop where the space is reduced. So that's all about tail recursion. Now next we will see head recursion. Now let us see head recursion. See, this is a structure for head recursion. If there is a function that is calling itself, so it's a recursive function, then the first statement inside the function is recursive call. It is calling itself here. Then what all the processing it has to do, it is doing it afterwards, after the recursive call. So there is no statement, no operation before the function call. See, if there is something here, then it is not a head recursion, right? If something is there before the function call, just it is a recursion. We don't have to give any special name for that one. So there is nothing before that one, then we can say this is a head recursion. So what do you mean by head recursion? It means the function doesn't have to process or perform any operation at the time of calling. It has to do everything only at the time of returning. So all the processing is done at returning time. Then such functions are head recursion. So the example of this type of recursion already we have seen in the previous video. This was the simple example. So you can see that the function is first calling itself, then the second statement it is printing. So the printing will be done at returning time. So the function doesn't do anything at calling time. So such recursions are head recursion. Next, we will compare head recursion versus loop. Can we convert them into loop? Let us discuss this. I will try to write the same function using loop. So let me write here void function fun. Now instead of conditional statement, I have to write a loop that I already have shown you. So if n greater than 0. Now here first it has to make a recursive call, then it is printing. So if you remember the output of this one, the output of this function was 1, 2, 3, as it's going to print at returning time. So if you remember the answer in the previous video, or else you can check back, the result of this type of function is 1, 2, 3 because it is printing at returning time. Now as it is, I have tried to write the function with a loop. Now I want the output to be 1, 2, 3. So if I use printf here, printf %d n. Then if I am passing function fun with value 3, then first value of n will be 3. So 3 is greater than 0, yes. So it will print what? 3. It will not print 1. First value that will be printed will be 3. It is not 1. Then if I have to repeat, then just like this one, instead of that if I write n minus minus, then it doesn't work same as that one. So you cannot easily convert it. So you have to write it in some other way to get the same output. But as it is looking at the function, if you try to convert, it's not easy. We can write some function which prints 1, 2, 3 using loop, but looking at this function, we cannot directly create it. So it means I have to write it in a different way. So let me write it. Suppose I have to take some variable I, and that is value 1. Then I should say I is less than equal to n. Then here I should say I plus plus, and I should make this I plus plus after printf. So let us try to run and see this one. If I pass the value as a 3, that is n is a 3. So I is 1, 1 is less than 3, so it will print I, that is 1. So output is 1. Then I becomes 2, so 2 is less than 3, so it will print 2, so result is 2. Then I plus plus, I becomes 3, so 3 is less than equal to 3, so I is 3, so it will print 3. Then I plus plus, I becomes 4, 4 is not less than equal to 3, so it will not enter in, and it will finish the loop and it will come out. So the output is 1, 2, 3. So that's it. You can see that that function cannot be as it is converted. So head recursions, or if a recursive function has to do something at returning time, it cannot be easily converted in the form of a loop, but it can be converted. It doesn't look as it is. So that's all about head and tail recursion. In the next video, we will see tree recursions. In this video, we'll learn about tree recursion. So first of all, I will compare what is linear recursion and tree recursion. Let us see. See, a linear recursion, a function that is a recursive function, if it is calling itself only one time, you can see that the function is calling itself only one time, then it is a linear recursion. So already we have seen in the previous video that the functions which are calling just one time, and we have seen head recursion and tail recursion, but in this example it is having something to process before the call as well as after the call, so it is just a recursive function, right? We cannot name it as head or tail recursion. And this code is not a C or C++ code. I have just written a pseudo code here, so it's not a complete function like now integer, everything is not there. So don't try to read it as C language code. Just I am showing you structure. Then here, tree recursion. So what is tree recursion? If a function that is recursive function is calling itself more than one time. So here you can see it is calling itself first time, and here it is calling itself second time. So if a recursive function is calling itself more than one time, then it is tree recursion. So in my example, I have shown it as 2 times. So it may be more than 2 times also. So that we call it as tree recursion. So here I have one example of tree recursion which is similar to the previous examples, only the difference it is calling itself more than one time. So I will trace this one and show you how it will work and what will be the output, and also I will show you how the stack is created in this one. Let us look at the tracing of this function. The function is called by passing value 3. I have taken a piece of stack. I'm not taking complete memory, entire memory, just I am showing you stack, how it is used by this recursive function, which is a tree recursion. Let us trace. First it is called by passing function with value 3. So the first call is fun of 3. For this function, an activation record is created and the value of n will be 3. So this is the first record created. Then what are the steps it has to perform? First print the value, then make 2 calls. So it will print the value, then it will make 2 calls. Let us print the value. See, it will print the value 3 and make first function call fun for n minus 1, that is 2. And second call it has to make, that it will be doing once this call has finished. So let us first finish first call. So for this call, and again activation record is created where the value of n will be 2. Now for this call, let us see what happens. N, that is 2, is greater than 0. Yes, 2 is greater than 0. Print and then make 2 calls. So let us do it. Print 2 and make 1 call with n minus 1, that is n minus 1. So 2 minus 1, 1. Then second call it will make after finishing this one. So far we have 2 values printed. So I'll also be writing the output here. So the output of the function so far is 3 and 2. Now let us continue with this call. This call, again an activation record is created and the value of n will be 1. Now for the value of n is 1, 1 is greater than 0. Yes, it is greater than 0. Then it will perform 3 steps. First print 1, then make 2 calls. So first it will print the value that is 1. Then it will make first call with a reduced value of n. So this is 1, so it will be 0. And second call it will make afterwards. So for this call, again a fresh call is made from here. So a new activation record is created where the value of n will be 0. Now this time fun of 0, this is 0, 0 greater than 0, no. So it will not enter inside and it will not perform these steps. So the function call terminates. Now the function calls terminates, this activation record is deleted from the stack. So before deletion, if you count 1, 2, 3, 4, 4 activation records. How many calls? 1, 2, 3, 4. 4 calls. So 4 activation records are there. So this is deleted. Now once it is deleted, it will go back to the previous call. It means this has finished. It will go back to the previous call. In previous call, for performing 3 steps, first was completed, second is also completed just now, third one has to be performed. So it will make a call here for n minus 1. Next call, n minus 1. So n minus 1, 1 minus 1 is again 0. So again it will make a call with value of n as 0. So again the activation record is created. Actually this was gone. So new activation record is again created. So I have erased this one. So let us assume again it is created here. So now again the size of the stack is 4. Next, for fun of 0, this is 0. 0 is not greater than 0. So it's not going to enter inside. Function ends. So this activation record is deleted and this function terminates. So now you can see that for fun of 1, all 3 steps are completed. Printing, calling itself 2 times with reduced value of n. That is 1 is printed and 0, 0 is called and they have finished. And in the output we also have 1. Now this call is completed. All 3 steps are over. So it will go back to the previous call. So go back to the previous call means this call has finished, means this activation record is deleted. So right now there are only 2 activation records in the stack. One is for value of n as 3 and value of n as 2. Now it is back on this call where n is 2. And in that, out of 3 steps, it has already performed first step, printing of 2 and call. Then the next, again it has to make a call, that is n minus 1. So now it will make a call for fun of n minus 1. So again fun of n minus 1, that is 2 minus 1, that is 1. Now again a fresh call. So new activation record is created. Now for this it is 1, so it will print 1. Now all these things that happens will be similar to this one. So it means it will print 1 and then it will call itself for, now I will not write complete name fun, I am just using f because of lack of space. f of 0. So this activation record is created again. Then this ends, so this is deleted, then goes back, again call for 0. So again an activation record is created for 0 and this ends and this is deleted. Now control goes back to this is finished, goes back to this, all three steps are finished, then goes back to fun of 3. In this it has to perform one more step, that is fun of, this was 2, so this is also 2. So 3 minus 1, 3 minus 1. So again 2 calls are made. So already this portion we have seen it completely. Same thing happens here also. Here also same thing happens. Now this I have taken enough space for explaining this one. Now this I have to write it in small size, but it will happen as it is what has happened here. So let me finish it quickly. So the first thing happened is value 2 is printed. 2 is printed. And here activation record is created. Then call for fun of 1. New activation record for, this was gone, sorry. So 1 is created. Then for this value 1 is printed. Value 1 is printed. Then call for fun of 0. And this ends. Activation record one more is created with value 0 and this ends. And again a call for fun of 0. Again and 0 and this also ends. This also goes back. Here fun of 1. For this 1 is printed. So output is 1. Then call for fun of 0, call for fun of 0, right? So again 2 more activation records, then that also finished, this also finished, and finally 3 also finish. So this is the output that we get. So I have simultaneously shown you how the activation record works. So you can see that maximum size of the stack was how much? 1, 2, 3, 4. Maximum was 4. 1, 2, 3, 4. And total how many activation records are created? As many calls are there. Right? I did not draw all, just I have given the idea. I did not draw each and every call here. So if I count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So total 15 calls are there. So 15 times activation records are created and deleted. Now I will remove this stack and redraw this tree once again and we will analyze more on the tree. I have redrawn the tree once again. Let us analyze the tree, so by which we can analyze the working of this recursive function. So here is a tree. Now first of all, let me label the calls in which order they are called. See, the first function call is this one, 1. Then second call. This will be done once this has finished. It has to finish. So under that there are 3 things again. So second call, printing is done. Then third call. Then this one will be done once this has finished. So under this printing, then this call, fourth call. Now this is fun with value 0. This will terminate. Then it will go to this call. So this is fifth one, fifth call. Then as this has finished, it will go back and then it will make this call. So this is sixth call. Then under this 7th and 8th. Now these are also finished. So under this, if you see, all the calls are completed. Now it will go to this one. So this is the 9th call. So that is the 9th call. 9th activation record to be created in the stack. Now height is how much? 1, 2. So only 2 will be there in the stack. But the count, if you take this, the 9th one. So this is 9th call. Then under this, printing is done and this call is made. So this is the 10th call. And then printing is done and this is made 11th call. And this will finish now because value of n is 0. Then this call, 12th call. So this is also finished because the value is 0. So this will also complete. All 3 steps are completed under this one, 12th call. Then go back for this one, right side. 13th call, then 14th call and 15th call. So that's what already I have counted them. So total 15 calls are made in this particular function when we pass the value as a 3. So I have shown you the order in which the calls are made. This is very important for you to visualize or trace how these type of functions work, which are calling themselves more than one time. Now we will analyze the time complexity. So time complexity depends on the number of calls. Yes, in each call it is printing, except in the calls where the value is 0. So otherwise it is printing almost for every call. Then, now let us see how many calls are made if the value is 3. So for n, how many calls will be made? With that we can decide the time complexity of this one. So let us analyze this one. So if I count the number of calls level wise, then in this level just one call is made. And in this level if I see 2 calls are made, 2. And in this level 1, 2, 3, 4 calls are made, 4. And this level 1, 2, 3, 4, 5, 6, 7, 8. 8 calls are made. So it means when I have passed the value as a 3, then in the first level 1 call, next level 2 call, next level 4, then next 8. For 3 there are 4 levels. And if the value of n that I am passing here, this value n, if it is 4, then there will be 5 levels. It means the tree will be more bigger than this one. Then how many calls it may be having? So let us analyze this one. So for any value of n, how many calls it will be? So let us sum up all these. So I will take the sum of all those. 1 plus 2 plus 4 plus 8. This is total 15. Yes, we know this. Count all of them, that is 15, or you have add all these, you get 15. So this is nothing but 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3. So this is nothing but sum of the terms of, that is summation of terms of series, that is GP series, that is sum of geometric progression terms. What is all that GP series and all, we will learn some other time, but right now I'll just write on the formula. So this will be nothing but 2 power, highest term is 3, so this is 3 plus 1 minus 1. So it means if I have 2 power 0 plus 2 power 1 plus 2 power 2 goes on to, if this is n, then this will go till 2 power n. Then how much that is? This is 2 power n plus 1 minus 1. So that many calls it will make. So what is that equal to? So this is order of 2 power n. So total 2 power n calls are made. So if I substitute the value of 3 here, so 2 power 3 plus 1, 4. 2 power 4 minus 1, that is 16 minus 1 is 15. So for any value of n, the number of calls will be order of 2 power n. So that's all. We have seen what is tree recursion, and we have taken one example, and we have seen how the tracing tree is generated and how the calls are made, how the stack is used, and what is the time complexity. So for this example function, it was 2 power n. So it depends on the function what time complexity you may be getting. It's not that every tree recursion will have 2 power n. For this function, it is 2 power n. So the time is order of 2 power n. Then what is the space? What is the space complexity? So it depends on what is the maximum height of the stack, because total activation records depends on number of calls, but how much space it was occupying inside the stack. So you have observed that same space was reused inside the stack. One activation record was gone and the same place another activation record was created. So we don't require much space, just like 2 power n, but we require the space equal to the height of a tree that we got here. So 1, 2, 3, 4. If it is 3, 4 is the space. So if it is n, n plus 1 will be the space. So it is order of n. Space complexity is order of n. So maximum stack size that we need is n. That will be sufficient. So that's all about tree recursion.